Now we'll begin Chapter 4, Gradient-Based Methods for Optimization. Optimization is a branch of R&D that aims to find the minimizer or maximizer of given function. An optimization problem is the problem of finding the best solution from all feasible solutions. In this chapter, we'll study the gradient descent method, Newton's method, and their variants. Let's go to section 4.1, gradient descent method. The method was suggested by Cauchy in 1847. He was a French mathematician and physicist. It is invented for solving quadratic problem of 6 variables, but today the method can be comfortably used for solving problems of thousands of variables or billions of variables. Here we define optimal problem. Let omega be a subset in d-dimensional space. Now, given a function defined on omega, the problem of finding minimizer of f is formulated in this way. Minimum x in omega, f of x. Here f is the objective function and sometimes called the loss function and or cost function. And omega is the domain, or we call it the constraint set. We first consider a popular function used in machine learning community. A Rosenberg function in two-dimensional space is defined as here. If you plot the function, then you can see here the surface plot and contour plot. And this one is popular. The reason is now, okay, the minimizer is 1 and 1, so that is here. And around the minimizer, and this directional change of function is rapid. However, along that direction, and the solution is the function is not changing much. It makes a curved valley. So optimizing this function is not trivial. So it is quite challenging function. And also, the function is included in the SciPy optimize packaging. So if we call scipy.optimize.rosen, then you are accessing the function. And also its gradient and Hessian are available. So the function is quite popular. Usually, the function is used when you are trying to comparing the performance of your new algorithm or various optimization algorithms. Okay, and Rosenberg function can be defined in general dimensions. In 3D, it is given this form, and in general ND, you can formulate in this way. Here, x1 to xn are coordinate variable. You can see the detail from the Wikipedia. Okay, here we have a recall for gradient. The gradient is a vector pointing the direction of greatest increase of the function. And also if the function has local maxima or local minima, then at the point, the gradient must be 0. In the gradient descent method, we are using negative gradient for the direction and of marching direction. So minus negative gradient is the steepest descent direction, and using that vector, we try to march the points. For instance, for initial point x0, we are measuring the gradient at the point, and its negative is scaled by gamma and added to get new point. Here the goal is, at the new point, the function value is smaller than the value at the earlier one, once it is not the local minimum. Here we define the gradient descent algorithm in this format. Given an initial point x0, iterate xn plus 1 recursively using the formula. And here, the parameter gamma, positive, is called the step length or the learning rate. In practice, gamma must be chosen small. If you choose it carelessly, then often the gradient descent method blows up. Now, to understand the method better, let's try to deal with easy problem, unconstrained minimization problems defined in one-dimensional space. Okay, here we have the gradient descent method in 1D. Then the minimization problem is given in this way. Minimize over x, f of x. X is in a closed interval. Then the gradient descent method can be formulated in this way. Now, let's do some analysis to find a reasonable gamma. And through the analysis, we'll get some good information and useful for some generalization of the gradient descent method. Okay, here we start with Taylor's theorem. F of x plus t, and if it is expanded about x, then now f of x and t f prime x, and this remainder, that is a remainder of integral form, but you may use a more popular form. Okay, rather than this integral form, remainder can be written this way. That is now here, okay. Rather than this one, you can use here t squared over 2 factorial and f double prime at some point. Okay, that is Taylor theorem. Okay, now we assume that f double prime is bounded by L. Then now here that is bounded by L, so that if you replace that one by L, then you can reach this inequality. Now we are using x is xn and t is minus gamma f prime xn. Then now x plus t will be this one, and that is same as xn plus 1. Now by using this inequality, we are reaching at this one, and now algebraically we can get that one. To make it as small as possible, first of all, this term must be positive and that must be maximized, because they are already determined the point, determined the values, and we have to maximize by choosing gamma Okay, here the positiveness is required, and then that is the same as now gamma is between 0 and L over 2 over L. So is maximized when we are choosing mid value. So gamma is 1 over L. Here, by using this one, you can rewrite the gradient descent method. Here we have, so gamma is replaced by 1 over L, and now L is maximum of f double prime in modulus. Okay, now furthermore, if we are using this and along with gamma replaced by 1 over L, now if you do some manipulate, then you can easily get this inequality. So it'll be used later quite effectively. So I highlighted with a yellow pen. Okay, here we'll see convergence of gradient descent method. Now, obviously, the method is producing a sequence of points, and along with the f of xn decreases. Once f is bounded from below, then now here f of xn is converges, so that xn will converge. Let's say the limit is x hat here. Then now we can rewrite here now for this one now in this way, because f is now continuous. Once that is convergent, then now this subtraction will go to 0. So here that means that f prime at xn converges to 0. So we can now say that f prime at the limit x hat is same as here, and then now that one is now here, then limit will go out, and so eventually here, because so that one will be 0, because already we know that f prime xn approaches 0, so that here 0. That means x hat is a critical point. So we can conclude that the method is converging to a critical point. Okay? But here it is it may be a local minimum or a saddle point, but at this level we cannot decide. However, anyway, it is converging to a critical point. From analysis, we can see that. Okay, this is the part 1. Now we'll continue in the second part. Thank you.